Okay, today we're going to see how derivatives can help us model motion in a straight line. Suppose we have a particle P, and it's moving along a straight line, in this case horizontal. S of t represents the distance P is from the origin in any time t during the movement. In this case, S of t is what we call a displacement function. It shows the position of the particle, in this case P, at a particular point. So if S of t is greater than 0, our particle is to the right of the origin at that time t. And if S of t is equal to 0, point P is at the origin. And if S of t is less than 0, P is left of the origin. So S of t represents again the position of the particle at any particular time. Now if we look at the change of the position over change in time, in other words, if we look at the position at time 2 minus the position at time 1 divided by time 2 minus time 1, change in position over change in time is what we call velocity. And so in this case, it would be the average velocity between these 2 points in time. Time t equals t2 and t1. So if we were thinking about our graph, we would be finding the gradient of the secant that connects these 2 points. Now if we want to find the velocity at any instant, or the instantaneous velocity, the instantaneous velocity is the limit as h approaches 0 of s of t plus h minus s of t over h, or what we've come to know as the derivative of s. So our velocity is equal to the derivative of our position function. So if I want to find a velocity function, all I need to do is to take the derivative of the position function. That will tell me the instantaneous velocity. That's the velocity at any particular time. And it would also, in terms of a graphical view, represent the slope of the gradient of the tangent line. Now if we look at change in velocity, velocity at time 2 minus velocity at time 1 over time 2 minus time 1. Well, that's just taking some fixed values and working them. And this would be called average acceleration. If we want the acceleration at an instant, the instantaneous acceleration, that's equal to the limit as h approaches 0 of v of t plus h minus v of t over h. And so our acceleration function, a of t, is equal to the derivative of velocity, which would mean it's going to be equal to the second derivative of our position function s of t. In this situation, we have a particle that moves in a straight line with a displacement function of s of t equals t squared plus 3t minus 2 meters, where t is greater than 0, t in seconds. Find the average velocity from t equals 1 to 3 from the average velocity of t equals 1 plus h. Find the value of the limit of s of 1 plus h minus s of 1 over h and comment on its significance. And find the average velocity of the particle. So first off, part A. Well, the average velocity is going to equal s of 3 minus s of 1 over 3 minus 1. So it's going to be 16 minus 2 over 2. So 14 over 2. It's going to be 7 meters per second. And letter B, to find the average velocity from t equals 1 to t equals 1 plus h, we're going to have to do s of 1 plus h minus s of 1 over 1 plus h minus 1. Well, in the numerator, we have to put 1 plus h into s. And then s of 1 again was 2. And my denominator simplified down to 2, just to h, because 1 minus 1. So we have 1 plus 2h plus h squared plus 2 plus 2h minus 2 minus 2. All of this is over h. And that's going to give us h squared plus 4h. And then we're going to have minus 1 over h. So that's what our average velocity would be between any two particular times. So on the previous one, h was 2 because we went 2 bigger to get from 1 to 3. So if we plug 2 in here, we would have 4 plus h minus 1 over 2 and it should give us 7, but something's not working here. Oh, this is a 3. Hopefully you caught that before me. So that's going to be 3 plus 3h. So it's going to be h squared plus 5h. And then we have 3, 4, so we're going to have 0 here. And so that's going to give us 4 plus 10, so 14 over 2 is 7 again. Now to letter C to find the limit of the expression. So in letter C, we're doing a limit as h approaches 0 of s of 1 plus h minus s of 1 over h. Well, that limit is familiar. That limit is the derivative. So this is really telling us to find the derivative evaluated at 1 and the derivative of our function. The derivative is going to be 2t plus 3. Go back and double check. So t squared plus 3t, 2t plus 3. So s prime of 1 is going to equal 5 meters per second. And in letter D, they wanted as t plus h. So s of t plus h minus s of t, our old first principles here. H approaches 0. We have t plus h squared plus 3 t plus h minus 2 minus t squared plus 3t minus 2. That's all over h. Algebraically, we have t squared plus 2th plus h squared plus 3t plus 3h minus 2 minus t squared minus 3t plus 2 all over h. In this case, the t squareds are going to reduce. The 3t's are going to reduce out, and the 2's are going to reduce out. And so we're going to be left with the limit as h approaches 0 of 2th plus h squared plus 3h all over h. We can factor out a common h and reduce it with the denominator, so we have the expression 2t plus h plus 3. And as h approaches 0, this approaches 2t plus 3. So this would be our derivative function. This would actually be our function for a derivative, which we found up here as well. So we now have connections between s of t, the position function or the displacement function, v of t, the velocity function, and a of t, the acceleration function. When we ask for initial conditions of any of these, we're asking for s of 0, which would be the position of p at time 0. V of 0 would be our initial velocity. And a of 0 would be our initial acceleration, our acceleration at time 0. These three tables are found in your textbook, but they give you interpretations of the signs of our different functions. We've already looked at the first one, when displacement is equal to 0, greater than 0, or less than 0, and how we interpret those time periods. When velocity is equal to 0, we've mentioned that that's velocity equaling 0 is going to mean the particle is at rest. When it's greater than 0, means the particle is moving to the right or up if we're talking about movement along a vertical line. And p is moving to the left when it's less than 0. And acceleration, when it's greater than 0, the velocity is increasing. So as we're going from 20 miles per hour to 30 miles per hour, we are accelerating. We're still moving to the right, but we are accelerating. Velocity is decreasing when acceleration is less than 0. So in a car, when we're slowing from 50 down to 35, we're still moving to the right, so our velocity is still positive, but our acceleration is negative. And velocity can be at a minimum or maximum whenever acceleration happens to equal 0. Here's a table that tells you different things. For initial conditions, we put 0 in for t. To find out when a particle is at the origin, you set your position function equal to 0. To find out when a particle is stationary, set velocity equal to 0. Also, when it's equal to 0, it could mean that a particle is changing direction, but we have to have a change in our sign of velocity, because it could just slow down, come to a stop, like in a rest area, and then just keep continuing traveling in the same direction. So particles can do that same thing. And when velocity is equal to 0, we could have a maximum height also. And it could also say minimum height in some situations. When acceleration is equal to 0, we have a constant velocity. And acceleration equals to 0 means that we have a potential for a minimum or maximum velocity. And again, we need to have a sign diagram of the acceleration function to determine whether the point's a maximum or minimum. What we mean there is here at this particular value of t, acceleration is 0. It's positive on this side, negative on this side of that point. And that tells us whether we're going to have a minimum or maximum at that particular point. We'll discuss that a bit more later this week. Now, with velocity, another word that's often used is speed. Speed is a scalar, unlike velocity, which is a vector. It has direction and magnitude. Our speed at any time t is equal to the absolute value of the velocity of t. And another way we can determine some things about speed, are we speeding up or slowing down? We know a speed, but is it we're speeding up or slowing down? If velocity and acceleration have the same sign, so if they're both positive or both negative at a particular value of t, then we are speeding up. And if velocity and acceleration have different signs, we are slowing down. Now make sure that on page 6, it's 34, example 4. Let's change it to 632. Example 4, look at that example of how we can use the information that we've just talked about with our derivatives to find what we need to know about speed, velocity, and acceleration. So our assignment is 21C.1, number 2, 21C.2, 1, 2, 3. You can use the magic book if Bob doesn't give you enough help, but please make sure you go to Bob before you use the magic book. Thank you. Talk to you tomorrow.